This is the beginning of a new section. This is section 4.2, which is titled the exponential distribution. Here is an analogy. In your first course in statistics, you might have recognized that the normal distribution plays a pivotal role, and the reason for that is the central limit theorem. Likewise, in reliability and survival analysis, the exponential distribution is going to play a pivotal role, and that is because it's the only continuous distribution with a constant hazard function. Now, the exponential distribution also shows up in a sub-area of operations research known as queuing theory. In queuing theory, the exponential distribution is used to model the time between arrivals and oftentimes the service time as various waiting line scenarios arise. The exponential distribution is often used for modeling of electronic components, and in fact there is a military standard numbered 217 that contains failure rates for various electronic components. The exponential distribution is mathematically tractable, so if you look at the lifetime distribution representations at the bottom of this slide, you'll see they all have nice functional forms. In addition, the exponential distribution has statistical inference techniques which are particularly tractable. So it is very easy to fit an exponential distribution to a lifetime data set. Next, the exponential distribution has a single positive parameter lambda, and that lambda is known as the failure rate in reliability work. Now, in other fields like in queuing theory, lambda will be known as the arrival rate for customers arriving to a queue. It can also be known as the service rate. The units on lambda are the number of failures per unit time. There are two different ways to parameterize the exponential distribution. The first way is to use lambda, and that's the more frequent of the two, and in that case lambda is a failure rate. But it's also possible to parameterize it using theta, where theta is the population mean of the exponential distribution. We will do that occasionally in Chapter 7. Keep in mind that the exponential distribution has a very restrictive modeling assumption, and that modeling assumption is a functioning used item and a functioning new item have the same distribution for their times to failure. Finally, if t is greater than or equal to 0, here are the 5 lifetime distribution representations for the exponential distribution, and you'll notice that these are particularly mathematically tractable. Here are pictures of the 5. The first in the upper left here is the probability density function, time of course on the horizontal axis. This is given for a failure rate of 1 and a failure rate of 2. The next one is the survivor function, and it won't surprise you that the survivor function associated with lambda equals 1 is higher than the survivor function for lambda equals 2. If we have a failure rate, and let's just use hours here, of 1 failure per hour versus a failure of 2 failures per hour, we would assume that the item with 1 failure per hour will always have a higher survivor function, so that should not be surprising. For the hazard function for lambda equals 1, of course, the hazard function is constant at 1, and lambda equals 2 corresponds to an item that is at higher risk, so in that case, lambda is equal to 2. The cumulative hazard function is the integral of the hazard function, so of course the integral of a constant function is linear, and here is that function for lambda equals 1 and for lambda equals 2. Finally, for the mean residual life function L of t, in the case of a failure rate of 1, the mean time to failure will always be 1, and that's for a brand new item at time 0, but it's also for a used item here at, it looks like, time 1.1. However, for the item with a higher failure rate of 2, the mean residual life will be shorter, and in this case the mean residual life is the reciprocal of lambda, so it will be constant at 1/2. The exponential distribution has a lot of different properties, and we're going to go through them one by one. Sometimes they will be proven, sometimes just stated. The proofs are all contained in an appendix in the book, and I encourage you to look at those proofs if they are not given here. So the assumption here is that the non-negative lifetime t has the exponential distribution with parameter lambda, and that lambda is the failure rate. The shorthand for this is as follows: t and then a tilde or a squiggle exponential lambda, and the way you read that is the random variable t is an exponential random variable with positive failure rate lambda. Here is the first result, and this is known as the memoryless property. If t has an exponential distribution with parameter lambda, then this left-hand side, probability that t is greater than or equal to t, which you may recognize as the survivor function, is the same as this basically conditional survivor function, and that's for any positive value for t and any positive value for s. The thinking here is that the conditional survivor function for a lifetime of an item that has survived to time s, that's right here, is identical to the survivor function for the lifetime of a brand new item. So from that thinking, you could ask the question, is the exponential distribution a good model for people? Do people not age? No, of course they do age, and as you get older, you are more susceptible to disease. How about for a candle? Would you trade in a brand new candle for a used candle? No, that used candle might be just a little bit of a stub. You would take the new candle. How about a heat pump? Would you take a new heat pump or a used one? I'd prefer a new one. How about a battery? Would you want a brand new battery or would you want one that's halfway drained down? I'd take the new one. So you can see this is a very, very restrictive assumption. One case where you might say it doesn't matter if you get a used or a new item is a fuse. A fuse does not degenerate typically over time, and so a used fuse might be as good as a new fuse. Here is the picture associated with the memoryless property. First of all, here you have the survivor function of a new item, and here you have the survivor function of a used item. If the memoryless property applies, then what you can say is if I take this second survivor function for the used item and I were to take it and shift it to the left, it would fall right on top of the survivor function for a new item. And that is to say, a used item has a conditional lifetime distribution, which is identical to a new item. And once again, the exponential distribution is the only one, the only continuous distribution with that property. Finally, here is a proof of the memoryless property since it is fairly fundamental to working with the exponential distribution. The conditional probability of surviving to time t plus s, given you have survived to time t, is the probability of t being greater than or equal to t plus s divided by the probability of t greater than or equal to s. That is simply by the definition of conditional probability. If you have the probability of one event given another event, that is the probability of the intersection of those two events divided by the probability of the given event, and that's exactly what we've done here. So this first step is by the definition of conditional probability. Now the second step is to recognize that both the numerator and the denominator are the probability that t is greater than or equal to something. So once you recognize that, you know from the definition of the survivor function that the numerator will be s of t plus s and the denominator will be s of s. Then the next step here goes back to the assumption which says that these items are exponentially distributed, so we simply plug in the survivor function with an argument t plus s in the numerator and an argument s in the denominator, and you get this. Well, one step of algebra here will show you that the e to the minus lambda s in the numerator and the denominator cancel, and you're just left with e to the minus lambda t. But you recognize that e to the minus lambda t is the survivor function for the exponential distribution, and by definition of s of t, that is the probability that t is greater than or equal to t, which proves our result. This is one side of the memoryless property. This is the other side, so we have proven the memoryless property.